Think about the last staircase you used. Maybe it was in an office building, an apartment block, a shopping mall, a hotel, a school, or even an airport. You probably walked up or down those stairs without giving them a second thought. After all, stairs are just stairs, right? A few concrete steps, a handrail, maybe a landing in the middle, nothing particularly interesting. But here's a question. Why do most stairs feel surprisingly similar no matter where you are? Why isn't every architect free to make stairs any shape or size they want? Why are the steps usually a certain height? Why do some staircases seem extremely wide while others are narrow? Why do emergency stairwells hidden behind heavy doors? Why do tall buildings often have multiple staircases? And perhaps the biggest question of all, why do building codes spend hundreds of pages talking about something as simple as stairs? The answer is fascinating, because stairs are not just architectural features, they're survival systems. Every staircase inside a modern building is the result of decades, sometimes centuries, of engineering research, human behavior studies, accident investigations, fire science, and hard lessons learned from real disasters. What looks like a simple set of steps is actually one of the most carefully designed parts of any building. And today, we're going to uncover the hidden science behind it. Let's start with something that most people never notice. Imagine you walk into a building and see a staircase where every step is different. The first step is short, the second is tall, the third is even taller, the fourth is shallow. Sounds ridiculous, doesn't it? You'd probably trip before reaching the top. That's because the human body loves predictability. When you're climbing stairs, your brain quickly learns the rhythm of the steps. After only a few steps, your muscles begin moving almost automatically. You stop consciously thinking about every movement. Your body develops a pattern. Left foot, right foot, left foot, right foot. The moment that pattern is broken, accidents happen. That's why even a small difference in step height can dramatically increase the risk of tripping. In fact, studies have shown that people are surprisingly sensitive to inconsistencies in stair dimensions. A difference of only a few millimeters can be enough to cause someone to stumble. Think about that for a second. A tiny change that most people can't even see can completely throw off the body's natural movement. That's why stair design is far more scientific than most people realize. Now, let's look at another interesting question. Why don't architects simply make steps taller? If each step were twice as tall, buildings would need fewer steps. Construction would be cheaper. Space could be saved. Sounds efficient, right? Not exactly. Try climbing a staircase where every step reaches halfway up your knee. You'll immediately feel the problem. Your legs have to work much harder. Your balance becomes less stable. Older adults may struggle. Children may struggle. People carrying groceries may struggle. And during an emergency evacuation, thousands of people could move much more slowly. On the other hand, what if steps were extremely short? That doesn't work well either. People would have to take too many steps. Walking would feel awkward and unnatural. Instead of helping movement, the staircase would interrupt it. As we'll see later in this series, many stair dimensions are actually based on the natural proportions and movement patterns of the human body. In other words, staircases are designed around people, not around concrete, steel, or architectural aesthetics. But stairs aren't only about everyday convenience. Their real importance becomes clear during emergencies. Imagine you're on the 20th floor of a high-rise office building. Suddenly, the alarm goes off. Elevators stop operating. Smoke begins spreading somewhere in the building. At that moment, one thing instantly becomes more important than almost everything else: the stairs. Not the lobby, not the fancy glass facade, not the conference rooms, not the rooftop garden. The stairs. Because for most occupants, the staircase becomes the primary path to safety. This is why building designers treat staircases differently from almost every other space in a building. A meeting room can be redesigned, a lobby can be renovated, a restaurant can change layouts. But stairways are heavily regulated because people's lives may depend on them. And that's not an exaggeration. Many of the rules governing modern stair design were written after tragic events where inadequate exits contributed to injuries and deaths. Every major fire disaster teaches engineers something. Every evacuation reveals weaknesses. Every investigation leads to new questions. Could people escape quickly enough? Was the stairwell wide enough? Did smoke enter the escape route? Were exits easy to find? Could firefighters access the building effectively? Over time, these lessons became building codes. In a way, modern stair design is a giant collection of human experience. Some lessons were learned through careful scientific research. Others were learned at a much higher cost. Now here's something else most people never think about. Stairs serve different purposes depending on the type of building. The staircase inside a hospital is not designed exactly like the staircase inside a school. The staircase inside a stadium is different from the staircase inside an apartment building. And the staircase inside a super tall skyscraper is almost different from everything else. Why? Because people use buildings differently. A hospital may need to move patients on stretchers. A school may need to evacuate hundreds of students at the same time. A sports stadium may need to empty tens of thousands of spectators within minutes. A high-rise office tower may require firefighters to climb dozens of floors during an emergency. Each situation creates unique challenges, and each challenge influences the way stairs are designed. This is one reason why architects don't simply copy and paste staircases from one project to another. Every building has its own demands. Every occupancy type has its own risks. Every staircase must balance safety, efficiency, accessibility, and practicality. The result is something far more sophisticated than most people realize. In fact, some of the most important engineering decisions in a building are hidden inside spaces that occupants rarely admire. People often take photos of skyscrapers. They admire dramatic roofs. They praise beautiful facades. They talk about innovative structures. Almost nobody posts pictures of a fire stairwell. Yet, when things go wrong, that fire stairwell may become the most important space in the entire building. That's the strange thing about good engineering. The best designs often go unnoticed. When stairs are designed properly, people simply use them. Nobody thinks about them. Nobody complains. Nobody even notices the enormous amount of science behind them. But hidden inside every step, every landing, every handrail, and every fire-rated door is a story about human behavior, safety, and engineering. And once you start looking closely, you'll never see stairs the same way again. In the next part, we'll dive deeper into one of the biggest mysteries of stair design: why stair dimensions around the world are surprisingly similar, and how the human body itself determines the size of almost every step we climb. Take a look at almost any staircase you've ever used. Whether you're in an office building in New York, a hotel in Dubai, an apartment tower in Singapore, or a shopping mall in London, you'll notice something interesting. Most stairs feel surprisingly similar. The steps aren't identical, of course. Different countries have different building codes, and architects have some flexibility. But overall, the height and depth of stairs tend to fall within a fairly narrow range. That's not a coincidence. It's not because architects around the world copy each other. And it's definitely not because somebody long ago randomly picked a number and everyone decided to stick with it. The real reason is much more interesting. The human body is the designer. Long before building codes existed, people were already discovering what kinds of stairs felt comfortable and what kinds felt exhausting, awkward, or dangerous. Over centuries, builders learned through experience. Later, engineers and researchers studied human movement scientifically. Eventually, those observations evolved into the stair dimensions we use today. In other words, modern stairs are built around human biology. Let's see why. Imagine you're walking on a flat sidewalk. Your body naturally develops a rhythm. Each step has a comfortable length. Your center of gravity moves smoothly. Your muscles work efficiently. You can walk for long periods without thinking much about it. Now introduce a staircase. Suddenly, your body has a new challenge. Every step requires you to lift your weight upward against gravity. The higher the step, the harder your muscles have to work. It doesn't sound like much, but climb 10 flights of stairs and you'll feel the difference immediately. Gravity never takes a day off. Every inch matters. This is why stair riser height, the vertical distance from one step to the next, is one of the most important dimensions in stair design. If risers are too high, climbing becomes tiring. Your knees must bend more. Your leg muscles must generate more force. Your balance becomes less stable. Older adults may struggle. Young children may struggle. People carrying bags may struggle. And during an emergency evacuation, thousands of people could slow down significantly. Now let's go to the opposite extreme. Suppose risers are extremely low. That sounds easier, right? Not necessarily. You would need far more steps to reach the same height. Walking would start to feel awkward. Your natural stride would be disrupted. Instead of moving smoothly, you'd constantly adjust your rhythm. What initially seems comfortable quickly becomes annoying. That's why stair design is always a balancing act. Too high is bad. Too low is bad. Somewhere in the middle lies the sweet spot. And surprisingly, engineers figured out that sweet spot a long time ago. One of the most famous principles in stair design comes from a simple formula. 2r plus t equals approximately 600 to 650 millimeters, where r is riser height, t is tread depth. The tread is the horizontal part where your foot lands. This formula may look simple, but it contains centuries of observation about how humans move. Think about what happens when you climb stairs. Each step upward requires both a vertical and a forward movement. The riser controls the vertical effort. The tread controls the forward distance. Together, they create the rhythm of walking. The formula essentially tries to make stair climbing feel as natural as possible compared to normal walking. When architects choose dimensions that fit this relationship, stairs feel comfortable. When they don't, people immediately notice something feels wrong, even if they can't explain why. Have you ever walked up a staircase that felt strangely steep, or one that seemed unusually shallow? You probably sensed the problem within seconds. Your body noticed before your brain did.
That's because humans are incredibly good at detecting movement patterns. We're constantly predicting where our feet will land. We're constantly adjusting balance without conscious thought. Good stair design works with those instincts. Bad stair design fights against them. And when a staircase fights against the human body, accidents become more likely. This brings us to another critical concept: consistency. If there's one thing engineers hate in stair design, it's inconsistency. Imagine a staircase with 20 steps. 19 steps are exactly the same height. One step is slightly taller, maybe only half an inch taller. Most people wouldn't even notice it by looking at it. Yet that tiny difference can dramatically increase the risk of tripping. Why? Because after a few steps, your brain starts operating on prediction. Your muscles memorize the pattern. You stop consciously measuring each step. The staircase becomes automatic. Then suddenly, one step breaks the pattern. Your foot expects one thing and encounters another. That split-second mismatch is enough to throw off balance. This is why building codes place strict limits on variations between steps. Uniformity isn't just about appearance, it's about safety. In many ways, a staircase functions like a machine, and machines work best when every component behaves predictably. Now, let's talk about something most people overlook: stair width. Why aren't all stairs the same width? Again, the answer comes back to people. Imagine a narrow staircase in a small house. Only a few people use it at a time. A modest width works perfectly fine. Now imagine the staircase inside a sports arena holding 50,000 spectators. The situation changes completely. Thousands of people may need to leave simultaneously. A narrow staircase would create dangerous bottlenecks. Evacuation times would increase dramatically. Crowding could become a serious hazard. This is why larger buildings generally require wider stairs. The width isn't chosen simply for comfort. It's calculated based on how many people may need to use the stairs, especially during emergencies. Engineers often refer to this as occupant load. The more occupants a building contains, the greater the capacity required for safe evacuation. In other words, stair width is really not about architecture. It's about human flow. Think of people moving through a building like water moving through pipes. If the pipe is too small, flow becomes restricted. If the staircase is too narrow, people cannot move efficiently. This becomes especially important during emergencies when every second matters. Now consider handrails. Many people think handrails are just optional accessories. In reality, they play a major role in safety. When climbing stairs, your body is constantly making tiny balance corrections. Most of the time, you don't notice them. But if you slip, trip, or lose balance, a handrail can stop a minor mistake from becoming a serious injury. For older adults, handrails are even more important. They provide stability, confidence, and support. That's why building codes often specify not only where handrails must be installed, but also their height, shape, and continuity. Even something as simple as a handrail is carefully engineered around human behavior. By now, a pattern is probably becoming clear. Almost every stair dimension exists because of people, not because of concrete, not because of steel, not because architects enjoy making rules. The height of steps, the depth of treads, the width of stairways, the placement of handrails, all of it begins with one question: how do humans move safely and efficiently? Modern staircases may look simple, but behind every dimension is a deep understanding of anatomy, biomechanics, balance, fatigue, and human behavior. The staircase is not merely a structure. It's a machine designed specifically for the human body. And once engineers figured out how people move, they could start solving an even bigger problem. Because comfortable stairs are one thing, safe stairs during a fire are something different entirely. In the next part, we'll explore why staircases need landings, why many buildings use U-shaped stairways instead of straight ones, and how these seemingly simple design choices can dramatically improve safety, movement, and emergency evacuation.
At first glance, a staircase seems pretty simple. You start at the bottom, you climb to the top. End of story. So here's a question. Why don't buildings just use one long, continuous staircase? Why stop halfway? Why add those flat platforms between flights? Wouldn't it be simpler to keep the stairs going in one straight line? It sounds logical until you actually try it. Imagine climbing from the ground floor to the 5th floor on a staircase with no landings at all. No breaks, no platforms, just one endless slope of steps. You'd quickly realize why engineers don't design stairs that way. The flat platform between flights is called a landing, and it does far more than most people realize. In fact, it may be one of the most underrated safety features in a building. The first reason is obvious once you think about it. People get tired. Even healthy adults experience fatigue while climbing stairs. Every step requires lifting body weight against gravity. The higher the building, the more energy that movement demands. A landing provides a natural pause point, not necessarily a place where people stop and rest completely, but a place where their bodies can briefly reset. The change from climbing to walking on a flat surface reduces physical strain and helps maintain a comfortable rhythm. This becomes especially important in taller buildings. Without landings, long stair climbs would feel significantly more exhausting. But fatigue is only part of the story. Landings also improve safety. Imagine someone trips near the top of a long staircase. Without a landing, that person could potentially fall a very long distance. The consequences could be severe. A landing acts like a safety barrier. It breaks a staircase into smaller segments. Instead of one continuous fall path, the staircase becomes a series of shorter segments. This dramatically reduces risk. Engineers often think about worst-case scenarios, not because they expect accidents to happen every day, but because when accidents do happen, the design should limit the damage. Landings are a perfect example of that philosophy. Now consider something else. People don't always use stairs under ideal conditions. Sometimes they're carrying furniture. Sometimes they're moving equipment. Sometimes they're carrying a child. Sometimes they're carrying groceries. Sometimes they're helping an injured person. A long, uninterrupted staircase becomes difficult to navigate in these situations. Landings provide maneuvering space. They create areas where people can adjust their grip, change direction, or allow others to pass. This is one reason moving a couch up several flights of stairs is difficult already. Imagine trying it without any landings at all. The experience would be miserable. Landings also solve another problem that many people never notice. Human beings aren't very good at seeing the end of extremely long staircases. When looking upward, a long staircase can appear intimidating. Psychologically, breaking the climb into smaller sections makes the journey feel more manageable. Instead of seeing one massive climb, people see a sequence of shorter climbs. The total height hasn't changed, the perception has. Good design often works that way. Sometimes the goal isn't just improving physical performance. Sometimes it's improving how people experience a space. This becomes especially important in emergency situations. During an evacuation, stress levels rise. People may be anxious, confused, or moving quickly. A staircase organized into shorter sections is generally easier to navigate than one massive, uninterrupted flight. The structure itself helps control movement. The flow becomes more orderly. The risk of panic-related accidents decreases. This leads to another interesting question. If landings are so useful, Why do staircases come in so many different shapes? Why are some straight? Why do some reverse direction? Why are others curved? The answer comes down to space, efficiency, and building function. Let's start with the simplest type, the straight-run staircase. This is exactly what it sounds like. One continuous flight moving in a single direction. Straight stairs are easy to understand, easy to build, easy to navigate. People instinctively know where they're going. For shorter vertical distances, they work extremely well. The problem appears when buildings get larger. A straight staircase connecting multiple stories can require a tremendous amount of floor space, and floor space is expensive. Architects are constantly trying to use space efficiently. That's where turning staircases become useful. One of the most common designs is the U-shaped staircase. You walk up one flight, reach a landing, turn 180 degrees, continue upward. This arrangement dramatically reduces the amount of floor area required. Instead of stretching across a long section of the building, the staircase folds back on itself. Many apartment buildings, office buildings, schools, and hotels use this configuration because it's compact and efficient. Then there's the L-shaped staircase. This design uses a 90-degree turn. The change in direction can help fit the staircase into awkward building layouts. It can also improve visibility and create a more interesting architectural experience. Rather than seeing the entire staircase at once, users discover it gradually. Sometimes functionality and aesthetics work together. Of course, not every staircase is designed primarily for efficiency. Some are designed to make a statement. Think about the grand staircases found in luxury hotels, museums, government buildings, or historic palaces. These stairs aren't merely transportation systems, they're architectural features. They're designed to impress visitors, to create drama, to establish a sense of importance. In these cases, the staircase becomes part engineering and part sculpture. But even the most beautiful staircase must still obey fundamental safety principles. The laws of gravity don't care how impressive a building looks. A staircase that photographs beautifully but functions poorly is ultimately a bad staircase. This is why engineers and architects must constantly balance appearance with performance. Now let's talk about one of the most controversial staircase types, spiral stairs. Almost everyone loves how spiral staircases look. They're elegant, they're compact, they're visually striking. They're popular in movies, luxury homes, and historic buildings. But from a practical standpoint, spiral staircases have limitations. The width of each step changes as you move toward the center. The walking surface becomes narrower. Foot placement becomes less predictable. Carrying large objects becomes difficult. Evacuating large numbers of people becomes inefficient. For these reasons, spiral staircases are rarely used as primary emergency exits in large buildings. They can be beautiful architectural elements, but beauty alone doesn't determine whether a staircase is suitable for life safety functions. And that brings us to one of the most important ideas in building design. A staircase is never just a staircase. Every decision reflects a specific purpose. The number of flights, the size of the landing, the direction of travel, the width, the shape, the location. All of these choices are responses to real-world problems. Engineers aren't asking, what shape looks cool? They're asking questions like, how many people will use this? How quickly can they evacuate? Can firefighters move through here? Can injured occupants be assisted? Can furniture be transported? Can the space be built efficiently? Can it remain safe for decades? Once you start looking at stairs through that lens, they stop being simple architectural features. They become carefully engineered systems designed to guide human movement under both normal conditions and the worst conditions imaginable. And nowhere is that more important when fire enters the picture. Because the moment smoke begins filling a building, the staircase transforms from a convenience into something far more critical, a protected path that may determine whether people get out safely or not.
If you ask most people what makes a building dangerous during a fire, they'll probably give the same answer: the flames. It seems obvious. Movies show giant walls of fire. News footage focuses on burning buildings. When people imagine a fire, they imagine heat and flames. But the reality is different. In many fires, the deadliest threat isn't the fire itself. It's the smoke. Smoke can spread through a building far faster than flames. It can reduce visibility to nearly zero. It contains toxic gases. It causes confusion, disorientation, and panic. In many major building fires throughout history, people never came into direct contact with flames at all. Instead, they became trapped by smoke. This simple fact changed the way engineers think about staircases. Modern stair design isn't just about helping people move between floors. It's about creating a protected escape route that remains usable even while the rest of the building is under attack. And that idea was written in tragedy long before it was written into building codes. For much of human history, fire safety was incredibly primitive. Buildings were often constructed from wood. Open flames were used for lighting and heating. Firefighting equipment was limited. Alarm systems barely existed. When a fire started, people often had only one option: run. The problem was that many buildings weren't designed for large-scale evacuation. Exits were inadequate. Escape routes were confusing. Doors opened in the wrong direction. Staircases became overcrowded. The results could be catastrophic. One of the biggest lessons engineers learned was that evacuation routes must remain protected even when the fire is spreading elsewhere. That sounds obvious today, but it took decades of disasters and investigations before this principle became standard practice. This is why modern fire stairwells often feel completely different from the rest of a building. Walk through a luxury hotel, you'll see expensive finishes, soft lighting, decorative walls, elegant furniture. Then open the door to a fire stairwell. Suddenly, everything changes. Concrete walls, steel doors, minimal decoration, a purely functional space. At first glance, it almost feels unfinished, but that's intentional. A fire stairwell isn't designed to impress anyone. It's designed to survive. Every element serves a purpose. The walls are built to resist fire for a specified period of time. The doors are designed to slow the spread of fire and smoke. The materials are selected because they perform reliably under extreme conditions. In many ways, the fire stairwell is like a fortress hidden inside the building. The goal is simple: protect the escape route long enough for occupants to get out safely. This brings us to one of the most recognizable features of modern high-rise buildings: the fire-rated stair door. Almost everyone has seen one. Heavy, self-closing, usually plain in appearance, often marked with emergency exit signs. Many people find these doors slightly annoying. They feel heavier than normal doors. Sometimes they close automatically behind you. Sometimes they seem unnecessarily robust. But every one of those characteristics exists for a reason. Imagine smoke spreading through a corridor. If the stairwell door remains open, smoke can quickly enter the staircase. Once smoke contaminates the staircase, the primary escape route may become unusable. The protected path is no longer protected. That's why fire doors are designed to close automatically. The building cannot rely on people remembering to shut them during an emergency. The system has to work even when occupants are frightened, distracted, or rushing to escape. Good safety design assumes that human behavior will be imperfect. Now, let's think about smoke itself. Smoke behaves differently than many people expect. Hot smoke rises. As it rises, it can travel through shafts, stairwells, elevator openings, and other vertical spaces. Engineers sometimes refer to this as the chimney effect. A tall building can unintentionally behave like a giant chimney. The taller the building, the stronger this effect can become.
Without proper protection, smoke can spread rapidly between floors. This creates a serious challenge. The staircase is supposed to be the safest place in the building during an evacuation, but the staircase is also a vertical shaft connecting many floors, exactly the kind of space smoke likes to move through. So, how do engineers solve that problem? One of the most effective solutions is something called stairwell pressurization. The concept is surprisingly simple. Instead of allowing air to flow into the staircase from surrounding areas, powerful mechanical systems push clean air into the stairwell. This creates slightly higher air pressure inside the staircase than outside. When doors open, air flows outward rather than allowing smoke to flow inward. The pressure difference may seem small, but it can dramatically reduce smoke infiltration. In effect, the building creates an invisible shield around its most important escape route. Most occupants never notice this system. They may walk through a stairwell their entire lives without realizing it's there. Yet during a fire, it can become one of the most important life safety systems in the entire structure. This illustrates a broader truth about engineering. The most important systems are often the ones people never see. Now, imagine a fire occurring on the 20th floor of a tower. Hundreds or even thousands of people may begin moving toward the stairs simultaneously. This creates another challenge. The staircase isn't only an escape route for occupants, it's also an access route for firefighters. While occupants are moving down, firefighters may be moving up. The same staircase must support two completely different flows of traffic: people escaping danger, people moving toward danger. Designing for that situation requires careful planning. Stair widths, landing sizes, door locations, and overall capacity all become critical factors. Engineers must think about movement under extreme conditions, not just normal daily use. A staircase that works perfectly on a typical Tuesday afternoon may perform very differently during a large-scale emergency. This is why fire safety engineers spend so much time modeling evacuations. They study how people move, how quickly they react, how crowding develops, how bottlenecks form, how smoke affects visibility and decision-making. Every improvement aims toward the same objective: giving people enough time to escape. Because in fire safety, time is everything. A few extra minutes can mean the difference between a successful evacuation and a tragedy. When people look at a staircase, they usually see concrete, steel, and handrails. Engineers see something else. They see a carefully protected survival corridor, a space designed not for everyday convenience, but for the worst day a building might ever experience. That's why modern stairwells often look so different from the rest of the structure. They're not trying to be beautiful. They're trying to remain functional when everything around them is failing. And that requirement becomes even more complicated when different types of buildings enter the equation. A hospital, a school, a hotel, a shopping mall, and a sports stadium may all contain staircases, but they face completely different evacuation challenges. The same basic principles apply, yet the solutions can look remarkably different.
At first glance, a staircase seems universal. People go up, people go down. Simple. So you might assume that once engineers figure out the ideal staircase, they can use the same design everywhere. But that's not how it works. In reality, one of the first questions architects and engineers ask is not, what kind of staircase should we build? It's, what kind of building are we designing? Because the way people use a building completely changes the way they use the stairs inside it. A staircase that works perfectly in an apartment building might be completely inadequate in a hospital. A staircase that performs well in an office tower might fail miserably in a sports stadium. The staircase isn't designed around the building, it's designed around the people inside the building.
and different buildings contain very different kinds of people. Let's start with one of the most challenging examples: hospitals. Most buildings are designed around people who can walk on their own. Hospitals are different. Many occupants cannot. Some patients use wheelchairs. Some are connected to medical equipment. Some are unconscious. Some may need to be transported on stretchers or beds. Immediately, the entire design problem changes. Engineers can't simply ask how fast healthy adults can move through a staircase. They must also consider patients, caregivers, nurses, doctors, and emergency response teams. This is one reason hospitals often have wider circulation spaces than many other buildings. Movement isn't just about walking, it's about transporting people who may be unable to move themselves. Fire safety planning becomes much more complicated as well. Evacuating a hospital isn't as simple as telling everyone to run downstairs. In many situations, patients are first relocated horizontally to safer areas before considering movement between floors. The building itself becomes part of the evacuation strategy. Now compare that with a school. Schools present another unique challenge. A typical school may contain hundreds or even thousands of students. Many are young. Some may panic during emergencies. Large groups tend to move together, and during class changes, hallways and staircases can become extremely crowded. If you've ever watched hundreds of students leave a classroom at the same time, you've seen how quickly pedestrian traffic can build up. Engineers must account for these peak periods. The staircase needs enough capacity to handle large flows of people safely and efficiently. The design must also be intuitive. Children should be able to understand where exits are without needing complicated instructions. When an emergency occurs, simplicity becomes a major advantage. The easier the route is to understand, the more likely people are to use it correctly. Now let's move to hotels. Hotels create another unique challenge. Unlike office workers, hotel guests are usually unfamiliar with the building. They may have arrived only a few hours earlier. They may not know the layout. They may not even know where the nearest exit is located. This changes everything. Office workers often develop familiarity through repetition. They use the same routes every day. Hotel guests don't have that advantage. As a result, hotels place enormous emphasis on exit signage, stairwell accessibility, emergency lighting, and clear wayfinding. The staircase must be easy to find even for someone who has never seen the building before. Imagine waking up at 3 a.m. to a fire alarm in a building you've never visited before. Visibility may be poor, stress levels may be high, people may be half asleep. The design must compensate for all of those factors. Now consider office buildings. At first glance, offices seem straightforward. Adults, predictable schedules, familiar occupants. But office towers introduce a different challenge: density. Modern office buildings can contain thousands of workers. Many arrive and leave around the same times. During an emergency, large populations may need to evacuate simultaneously. This is why office towers often require multiple stairways, not because one staircase can connect the floors, but because evacuation capacity matters. The goal isn't simply providing a path, the goal is providing enough path. A staircase that becomes overcrowded during an emergency can dramatically increase evacuation times. Engineers therefore calculate how many occupants a building contains and design exit systems accordingly. This process may sound technical, but the underlying idea is simple. The more people inside, the more exit capacity required. Now let's look at shopping malls. Shopping malls are fascinating because their population constantly changes. At any moment, visitors may be entering, leaving, browsing, eating, or gathering in groups. Many are unfamiliar with the building. Some are carrying purchases. Some are pushing strollers. Some are elderly. Some are small children. Unlike an office, the occupant population is highly unpredictable. Designing for that level of variation requires careful planning. Circulation routes must be obvious. Exit access must remain visible. Crowd movement must remain manageable even during busy periods. The challenge becomes even larger in entertainment venues. Think about a sports stadium, a concert arena, a large convention center. These buildings may contain tens of thousands of people, and unlike office buildings, those people often leave at nearly the same time. Imagine the final whistle of a championship game or the end of a sold-out concert. Suddenly, thousands of people begin moving towards exits. The staircase system must absorb an enormous surge of traffic. This is why stadium stairways often feel dramatically different from those in other buildings. They're wider, more numerous, designed to distribute crowds efficiently. Every minute saved can significantly improve safety and reduce congestion. Engineers often analyze crowd movement almost the same way transportation engineers analyze highways. Large numbers of people create flow patterns that can be studied, predicted, and optimized. The goal is preventing dangerous bottlenecks before they occur. Then there are airports. Airports combine many of the challenges we've already discussed: huge populations, unfamiliar occupants, luggage, multiple languages, time-sensitive movement, complex circulation patterns. The design must guide people smoothly through an environment that many are experiencing for the first time. Good airport design often feels effortless, but that effortless feeling is usually the result of thousands of hours of planning and analysis. What all these examples have in common is one simple principle: people shape buildings, not the other way around. When engineers design a staircase, they're not merely drawing lines on a blueprint, they're studying behavior, how fast people move, how crowds form, how fatigue develops, how emergencies unfold, how different populations respond under stress. The final staircase is really a physical response to those human realities. And that's why staircases vary so much from one building type to another. The dimensions may look similar, the materials may look similar, but the underlying design logic can be completely different. A hospital staircase reflects patient care. A school staircase reflects student movement. A hotel staircase reflects unfamiliar occupants. A stadium staircase reflects crowd management. An office staircase reflects evacuation capacity. Every staircase tells a story about the building it serves. The more closely you look, the more you realize that these aren't just collections of steps. They're carefully engineered systems designed around the behavior, limitations, and safety needs of the people who use them.
A staircase in a 3-story building is one thing. A staircase in a 100-story skyscraper is something else entirely. Most of the principles we've discussed so far still apply. People are still people. Gravity still works. Human bodies still prefer the same step dimensions. But once buildings become extremely tall, entirely new problems appear. Problems that simply don't exist in low-rise structures. And the higher a building rises, the more difficult those problems become. Think about it this way. Imagine you're standing on the 3rd floor of a building during an emergency. Walking down 2 flights of stairs isn't a big deal. Most people can do it in less than a minute. Now imagine you're on the 80th floor. The challenge changes dramatically. Suddenly, evacuation is no longer measured in seconds. It's measured in many minutes, sometimes much longer. Thousands of people may be trying to use the same stair system. Fatigue becomes a major factor. Crowding becomes a major factor. Smoke control becomes a major factor. Firefighter access becomes a major factor. The entire design philosophy changes. This is why engineers often say that skyscrapers aren't simply tall buildings. They're a completely different category of engineering. The staircase is one of the best examples of that difference. Let's start with a simple question. Why don't super tall buildings just use one giant staircase? The answer is capacity. Imagine a tower containing 10,000 occupants. If everyone had to use a single stairway during an emergency, evacuation would take an extremely long time. The staircase would become heavily congested. Movement would slow dramatically. People on upper floors might spend a very long time waiting. That's why high-rise buildings typically contain multiple protected stairways. Instead of relying on one escape route, the building distributes occupants among several independent routes. This improves evacuation efficiency and provides redundancy. If one route becomes compromised, others remain available. Redundancy is a core principle in safety engineering. Aircraft use it, power plants use it, data centers use it. Skyscrapers use it too. When human lives are involved, engineers prefer backup systems. One particularly clever solution is something called a scissor stair. At first glance, it looks like a normal stairwell, but inside the same vertical shaft are actually two completely separate staircases. They interlock with each other like the blades of a pair of scissors, which is where the name comes from. This design saves valuable floor space while still providing multiple protected exit routes. In a skyscraper, floor space is extremely valuable. Every square meter has economic value. The challenge is always the same. How do you maximize safety without sacrificing too much usable area? Scissor stairs are one example of engineers solving that puzzle. But evacuation isn't the only issue. There's also the problem of distance. Let's be honest, walking down 80 floors is hard. Walking down 100 floors is very hard. Even healthy adults experience fatigue after long stair descents. Now imagine elderly occupants, people with mobility limitations, people recovering from injuries, pregnant occupants, visitors unfamiliar with the building. The challenge becomes even greater. This is one reason many super tall buildings include refuge floors. These are specially protected floors designed to provide a temporary safe area during emergencies. Instead of requiring everyone to travel all the way to ground level immediately, occupants may move to a protected refuge area while emergency procedures continue. The exact implementation varies depending on local regulations and building design, but the underlying idea remains the same. Break a massive evacuation problem into smaller, more manageable pieces. Again, this is an example of engineers recognizing human limitations rather than pretending they don't exist. Another challenge unique to skyscrapers is smoke movement. Earlier, we discussed how tall buildings can behave like giant chimneys. In a super tall tower, that effect becomes even more significant. A small pressure difference over a very tall height can create powerful air movement. Engineers spend enormous amounts of effort controlling airflow within these buildings. Stair pressurization systems become particularly important. Ventilation systems become more sophisticated. Fire compartments become more carefully organized. The goal is always the same: keep escape routes usable for as long as possible. Because no matter how advanced a building becomes, people still need a safe path out. Then there's another issue most people never consider: firefighters. When firefighters respond to a low-rise building, reaching the fire may be relatively straightforward. But what happens when the fire is dozens of floors above ground? Carrying equipment up a skyscraper is physically demanding. Climbing floor after floor while wearing protective gear is exhausting. The building must support not only evacuation, but also emergency operations. This is one reason modern high-rises include dedicated firefighter facilities, protected communication systems, special access routes, emergency power systems, and increasingly, specially designed elevators that can assist emergency response under controlled conditions. That last point surprises many people. For decades, people heard the same rule: never use elevators during a fire.
As a general instruction for occupants, that's still sound advice in many situations, but modern high-rise engineering has become far more sophisticated. Certain elevators can be specifically designed and protected to support emergency operations. The goal isn't replacing stairs. The goal is supplementing them. Because once buildings reach extreme heights, relying exclusively on stairs becomes increasingly challenging. This reflects a broader trend in modern engineering. The solution to a problem is rarely a single system. It's usually multiple systems working together. Stairs, fire compartments, smoke control systems, emergency lighting, backup power, communication systems, protected elevators. Each contributes to the overall safety strategy. And that's really the biggest lesson hidden inside staircase design. When most people see stairs, they see a basic architectural feature, a way to move between floors, nothing more. But engineers see something very different. They see human behavior, they see biomechanics, they see crowd movement, they see fire science, they see risk management. They see decades of research and countless lessons learned from real-world experience. Every step height reflects how humans walk. Every landing reflects how humans tire. Every handrail reflects how humans lose balance. Every stair width reflects how crowds move. Every fire door reflects how smoke spreads. Every protected stairwell reflects a simple but powerful idea. People deserve a safe way out. That's why staircases are among the most heavily studied and carefully regulated elements in modern architecture, not because they're complicated, but because they're important. The irony is that the better a staircase is designed, the less people notice it. You walk up, you walk down. Everything feels natural. Everything works. And that's exactly the point. The best staircase is the one nobody thinks about, until the day it matters most.